The trapezium rule, the very last thing in the course, and it reflects the fact that, unfortunately, in real life, we can't always integrate to find the area under a curve, which is something that we all want to do. It's very useful in engineering and different fields, but quite often we don't know how to integrate, so we can't do it. So this is an approximate method, and you'll find the formula for it in the formula booklet, and it looks quite complicated, and it's up here at the top, all this thing here. The integral of y dx is approximately, with the wavy lines, equal to that thing there. It's actually not that complicated, and as usual a diagram helps us to explain it. So looking at this sketch that I've drawn here, the blue curve, let's suppose it has an equation, something horrible. It might be something to do with cos, which we don't know how to integrate yet. So we can't integrate, so we want to find the area by approximating it down to little trapezia, hence the name trapezium rule. So what we effectively do is between A and B we want to find this area between A and B. So we split it into several trapeziums, like so, and we then use that to approximate our area. So it follows, and you don't have to know this, that all of these different points are the y values that are in the formula, so y1 and y2, y3, etc. y0 is where A is, and yn is where B is. Get that in the right place. And when we're trying to work out the area of each trapezium, every single height, y1, y2, y3, all the way up to yn minus 1, are used in two different trapezia. So y1, for example, is used in this first one here, because it's one of the lengths of the parallel sides, and it's also used in the green one next to it, so it's used twice. So every sort of middle value of y, all these ones, are going to be used twice, and that's why we've got this 2 in our formula there. The y0 and yn are only used in one trapezium, so y0 is only used in the yellow trapezium, and yn is only used in this red one right at the end. So enough of that. Apart from to say that the width of each bar, or the width of each trapezium, the perpendicular height, is what we call h. So it has a complicated formula for h here, but basically what it means is the distance between B and A divided by the number of trapezia that we've got. So it's the width of each strip of under our curve. So h is just the distance from each x value to the next. So let's do an example. Let's look at exercise 11E, question 4. In the exam, you would normally be given a table, and the first part would be to fill in some of the table, and the second part would be to use the rule to find the area under the curve. So we're going to skip a little bit. Exercise 11E, question 4, all it says is find the area under the curve y equals 2 to the power of x between 2 and 0. So it effectively tells us to find this integral here. Integral 2 and 0, 2 to the x dx. Now, as we can't integrate 2 to the power x, or not yet anyway, this is why we've got to use a trapezium rule. Furthermore, it says to use 8 strips. So, because the distance between 0 and 2 is obviously 2 whole units, and we need to use 8 strips, we can quite easily, by common sense, work out that each strip must be 0.25. Again, you probably wouldn't have to draw this table yourself in the exam, but the ideas are not that complicated. So you go along then, put in each value of x into your calculator. So you do 2 to the power of 0 is 1, 2 to the power of 0.25 is 1.189, etc, etc. There's one here to do, so if you put in 2 to the power of 0.75, you should find that that gives you 1.682, which seems to make sense. It fits into the general scheme of things. And as always, we should draw a sketch. You should be able to draw this curve because it crosses the y-axis at the point 1, get it right, 0, 1. And because we're doing it over the range 0 to 2, let's try and draw it quite steadily. So it looks something like that. And then just a note about the end of the question. What we're doing is effectively dividing this into 8 different trapeziums. And you'll see, if you look really closely, that when we draw those trapeziums and it's more it's easier to see when we get into a steeper part of the graph. The trapezium, if we draw a blown up version of one of them here at the side, you'll see that the curve goes underneath the trapezium line. So the trapezium that we would use in pink is slightly bigger than the actual area under the curve, and therefore it's going to be an overestimate. Moving on then, let's use the formula. It looks complicated, it's not that bad. We simply substitute the numbers that we've got in. So a half times h, h is the distance between each x value, sort of the width of each strip, so that's 0.25. Then we've got actually two pairs of brackets here. They've used curly ones, but we'll use the big square ones. y0 plus yn, so the first and last y values, which are 1 here and 4 at the end, they're going to go in first because they're only used once. And then the rest of them, we've got another pair of brackets. All the other y values are actually used twice, as we explained previously. So 1.189 is the first one, and we keep going all the way up until we get to the last of those ones, which you can see from the table is 3.364. Close both sets of brackets, put them in your calculator, being careful to make sure that you get all your brackets in the right place, and you should end up with 4.34. So that is the approximate area under the curve, and as we discussed previously, if you look really closely at the trapeziums that you've used, you'll find that they're slightly bigger than the area under the curve, and thus part B of the question asks us whether it's an overestimate or an underestimate, and the answer is it's a slight overestimate of the actual area.